Now we're officially
Great.
starting.
So, this is Dr. Chavez,
Hello.
who some of you might know, is visiting scientific professor here this
Yeah.
year. And he's going to give us a talk about polynomial norms of graphs.
Yes, thank you. Polynomial norms of graphs. All right, so do not be intimidated. We're going to understand precisely what each of these words mean. Okay, so first thing I would like to do off the bat is thank you to my collaborators on this project, of which there are many. Now this project, I would say, encompasses some total of about five or six papers, I think. Now, each of these are, let me go back. Each of these are my co-authors on these 5 papers. And numbers in blue, not numbers, names in blue, these are undergraduate students, yeah? So what I'm talking about today is specifically the projects that I worked on with these undergraduate students, specifically the names in blue, right? So these are Sarah, Matilda, Kayron, Nethman, Justin, and Tyler, right? Okay, so we started working on this. It would have been the fall of 2022, and then we just finished up, we wrapped up this project. It was probably, I want to say, November of 23, so it was a year-long project. And each of these students were in my linear algebra class, and they stuck around to do independent study with me, and we solved an interesting problem. Okay, so we're going to do 3 things today. We're going to talk about, first off, of course, what a graph is. We're going to talk about how to measure the size of a graph. And then we're going to talk about the CHS norm of a graph, which is just a new way to measure the size of a graph. And then we're going to ask a very interesting question about finding the extremal graphs for these CHS norms. That essentially just means which of the graphs are biggest and which of the graphs are smallest. Where here, of course, by big and small, we're using this notion of a norm. Okay, so what is a graph? Essentially, it's just a bunch of dots with lines connecting them. This is an example of a graph. I have dots and I have lines connecting them. Now, the number of dots is called the order of the graph. And the dots themselves, we call them vertices, or sometimes we'll call them nodes. I'll use these terms interchangeably. Sometimes I'll say nodes, sometimes I'll say vertices. But just keep in mind, I mean dots. Okay. And one more thing that I would like to mention is the lines that are connecting these dots are called edges. So a graph, using this new terminology, right, is a collection of vertices with edges connecting them. Graphs can be connected or they can also be disconnected. This is an example of a graph that is not connected, and therefore we say it's disconnected. Why is it disconnected? It's because this vertex here, or node, right, doesn't have any edges connected to it. So this vertex is all by itself. This is a disconnected graph. Graphs, however, are not allowed to have loops for us specifically. Yeah. So for the purposes of this talk, our graphs do not have loops. So things like this are bad. We do not permit things like this. All right. Now, one interesting application of graph theory, in fact, some might say that network science, in fact, is applied graph theory. Yeah. In network science, what are we interested in doing? You're interested in studying things like biological structures, community structures, social structures. I use it a lot in statistical physics, actually, too. Now, the philosophy behind network science, essentially at the end of the day, is the following. Your nodes are going to represent agents, and edges represent a relation between 2 agents. Okay, so now in this next example, we're going to take a look at characters from season 2 of Game of Thrones. So I'm not sure if you've seen this before, but if you haven't, this would be a good introduction and hopefully motivation to go home and see it. Okay, so our graph here, right? We're going to construct a graph. Now again, in network science, the nodes represent agents. So here the agents are characters in season 2 of Game of Thrones. Yeah? Exactly. And then I'm going to draw an edge between 2 agents, or I'm going to draw an edge between 2 characters. If there's some sort of interaction between the characters. Yeah? Okay. Now, this is what you get if you do this. Yeah? Now, we've gone a little bit further here, and then we've actually done something called community detection. What we've done here is we've separated the nodes into different communities. Yeah. So the communities here are, how many are there? Let's count them. 1, 2, 3, 4, 5, 6 communities. Yeah. Now, the process of community detection, which is what we did here, essentially is the process by which you're maximizing edges within a community and minimizing edges inter-community or between communities. Yeah. Now, an efficient algorithm for being able to do this was actually only developed as late as it was 2008. Yeah, 2008. This algorithm was invented or discovered, right? Depending on your perspective. Me and Jim were just talking about this. Yeah. And yeah, so this algorithm was first invented in 2008 to be able to do this efficiently. That is, detect communities. And so if you run this algorithm on this network, this is the community structure that pops up. Yeah. So in this aspect, right, it's very interesting to study graphs. Right? Graphs are just a very, very interesting subject, and this is one example of how it's interesting. Yeah. So an important aspect, or one important question, I should say, that one would ask pertains to sizes of graphs. So here I'm going to show you two graphs, graph 1 and graph 2. And I'm going to ask you a simple question. The question is, which one of these graphs is larger? Yeah. The first thing you might want to do is count the nodes. Let's count how many nodes this has. 1, 2, 3, 4, 5, 6. 6 nodes here on the left. How about on the right? How many nodes are on the right? 6. There's also 6, right? So we can't say one is larger than the other based on the number of nodes because they have the same number of nodes. Yeah? Are there any other ideas of how we might measure the sizes of these graphs? There's lots of different ways to measure sizes. Yeah. Are there any other ones?
Yeah. Like the average degree.
Yeah, that's okay. So you can look at something called the degree, or the number of edges that connect a given vertex. Yeah. So for example, this graph here. So I'm pointing at this node right here. How many edges are connected to that node? Someone count for me. 5. Yeah. This is bigger than any vertex over here. The most you're going to get over here is 4. In fact, in this case, every vertex has 4 edges connected to it. Right? So in some regard, you might say, well, because 5 is bigger than 4, maybe this graph is larger. On the other hand, how many edges does this graph have on the right?
12.
This has 12, and this one has less than 12. I don't remember the exact number, but rest assured it's less than 12.
I think
Yeah?
it's 9.
Is it 9? Yeah, 9 edges, right? So depending on your perspective, you might say one is larger because it has a higher degree, this vertex here specifically. Or maybe this one's larger because it has more edges. Yeah? So it just depends on your perspective on how you're measuring quote-unquote length, or quote-unquote the size of a graph. Okay. So what we're going to do is we're going to talk about 3 different ways to measure the size of a graph. Yeah? There's these old classical ways, and there's these new ways, which that's what my research is about, is this new way to measure the size of a graph. So we're going to talk about these ways. Okay, so to talk about these ways, we have to kind of go back to our linear algebra and eigenvalues. Okay? What do we find eigenvalues for? We find eigenvalues of matrices. And so what I need to do is I need a way to construct a matrix from a graph. Right? So the idea is relatively simple. I have a graph. Right? Again, what is it? It's just a bunch of edges and dots, basically. Dots and lines. I have this graph. I take that graph and I construct a matrix from it. I take that matrix and I find its eigenvalues. And then after that, there's very natural ways that I can then determine the size of my original graph. And there's, again, 3 ways that I'm going to describe. Okay, so let's start with this example, this graph here. What's the order of this graph? It's 3 because I see 3 nodes. Okay, now what I'm going to do is I'm going to label the nodes any which way I want to. It doesn't matter how I order them. I could have chosen 2, 1, 3 or 3, 1, 2, it doesn't matter. Yeah? I'm going to do 1, 2, 3. Okay, now I'm going to construct a 3 by 3 matrix. I'm going to construct a 3 by 3 matrix precisely because this is a graph of order 3. And the way I construct this matrix, okay, vertex 1 is connected to vertex 2, right? So that means row 1, column 2 gets a number 1, right? So once again, Vertex 1 is connected to vertex 2. That means I put a 1 in the first row, second column of my matrix. And then what I'm going to do is I'm going to enforce symmetry by just going opposite the diagonal and also putting a 1 there. So once again, I have vertex 1 connected to vertex 2. That means the 1, 2 entry and the 2, 1 entry of my matrix is the number 1. Likewise, vertex 2 is connected to vertex 3. What does that mean? It means I need to put the number 1 in the second row, third column. And then on the flip side, also the third row, second column, because I want to enforce symmetry. And that is how I take my graph of order 3 and construct a 3 by 3 matrix. Yeah. And you can do this with any graph in the world. And in fact, this object here, right, which is called the adjacency matrix of the graph, determines the graph uniquely. Yeah? They're equivalent pieces of information. So I could take this matrix, and I can go backwards and draw what the graph has to look like. Or I can start with the graph and construct the matrix. So they are completely equivalent pieces of information. All right, so now generally, right, this was a very simple example. The general situation is as follows. What I'm going to do is I'm going to suppose I have G, a graph of order n. Right? So I have n nodes, and I have a whole bunch of lines connecting these nodes. The adjacency matrix, which I'll denote A, is the matrix A sub ij, defined as follows. A sub ij is 1 if and only if node I connects to node j. And then it's 0 otherwise. And that's the exact construction that we just went through. The eigenvalues of a graph. The eigenvalues of a graph are just the eigenvalues of its adjacency matrix. Right? So once again, I start with this graph. I construct its adjacency matrix. I look at the eigenvalues of the adjacency matrix. Right? And I remember that from linear algebra. I look at a characteristic polynomial for the matrix. And I find its roots, the roots of the characteristic polynomial. So those are the eigenvalues of my adjacency matrix. I'm defining those. Those are the things that I'm calling the eigenvalues of the graph. Okay. So, here's a nice example. Here's my graph of order 3. Like the most basic graph you can possibly have of order 3. Arguably. Well, yeah, I'd say so. It's pretty basic. There's not too many graphs of order 3. Okay, so I start with this graph. I build the adjacency matrix. I find the eigenvalues of this adjacency matrix. Yeah? You'll find that you have eigenvalues square root of 2, 0, and negative 2. So square root of 2, 0, and negative 2 are the eigenvalues of this adjacency matrix. Therefore, this graph has eigenvalues square root of 2, 0, and negative 2. Okay. Now, one really super duper important remark is that by the way these matrices are constructed, the fact that they're real and symmetric, this ensures that their eigenvalues are always real numbers. You know, we don't have complex eigenvalues here, precisely because the adjacency matrix is always going to be symmetric. And that guarantees the realness of the eigenvalues. Because in general, right, we don't necessarily have that, because we're finding roots of polynomials which could be complex. We don't have that. We have real eigenvalues. Okay. So now a norm gives us a way to measure the size of a matrix, essentially. So at the end of the day, a norm just gives us a way to measure the size of a matrix. Now, this way to measure a size of a matrix, in fact, generalizes our intuitive understanding of length in like R2, for example. Right? In R2, we know how to measure length. Right? If I want to measure the length of the vector 1, 2, well, I just sum the squares of the components, and then I take a square root. Right? In fact, it might be useful to write that formula down. Right? So, if I want to measure the size of a vector in R2, let's do this here. Oh no, this marker's dead. That marker fooled me. Here we go. Yeah, so if I want to measure, for example, the size of a vector, we'll call it V. Right? And we'll put a little arrow here. We like to do that sometimes. So V is the vector, we'll say x comma y. Living inside of R2. Right? It's just a nice vector in the plane. If I want to measure its size, or its length, one way to do this is just to sum the squares of the components and take a square root. Yeah. So a norm on the space of matrices, of all matrices, right? Essentially, it's just generalizing this idea. It's giving us a way to measure lengths, but not for vectors in R2, for vectors that are really matrices. Okay, yeah, so as I was saying, these adjacency matrices live in this vector space of n by n real symmetric matrices. And so if I have a way to measure the length, right, quote unquote, the length or the size of an n by n real symmetric matrix, I therefore get a way to measure the size of the graph. Okay, so there's the recipe. You start with a graph, you look at its adjacency matrix, and then you simply apply a norm to the adjacency matrix, which again is just a way to measure length. Okay, so let's cut down to the chase. How do I measure the size of a graph? Here's one way. This way is called the spectral norm. So I suppose I have a graph, G. One way to measure the size of G. And you know, one interesting fact is I'm using the same notation as I am over here. Right? Typically, lengths or norms are denoted with double bars like this. Yeah. So the size of the graph, right? So when you see this notation, it just means the size of the graph. Just think about it in that regard. So the size of the graph is the largest eigenvalue of the graph. So that gives us one notion of length for graphs, or size of graphs. And this is called the spectral norm. So the spectral norm of this graph here. What was the largest eigenvalue? If you remember from a couple slides ago, it was the square root of 2. Remember the eigenvalues were square root of 2, 0, and negative root 2. The largest of those is the square root of 2. So when I'm using my spectral norm ruler, right? We think of a norm as just as a ruler. I'm using my ruler to measure the length of this graph. It's going to tell me that it has a length of square root of 2, or the size is the square root of 2. Here's a different way, or a different ruler, if you will. Right? This gives me a different way to measure the size of a graph. This is called the Frobenius norm. I'm going to suppose I have a graph G, and the eigenvalues are lambda 1 through lambda n. And again, keep in mind these are real values. The Frobenius norm of G is it's essentially the analog of this to higher dimensions, really. In fact, it's induced by that norm on Rn. Yeah. Anyhow, the way I define the Frobenius norm of G, right, and I'm introducing different notation. I'm still using the vertical bars, but now I'm putting the subscript f to denote that it's a different measure of length. It's the Frobenius length, right? So this Frobenius norm is defined by taking the sum square, or taking the sum of the squares of the eigenvalues of the graph. Yeah. Let's go back to our example. This was my example that we started off with. What were the eigenvalues? They were negative root 2, 0, and positive root 2, right? So what is the Frobenius norm? Well, it's the square root of 2 squared plus 0 squared plus negative square root of 2 squared. What do I get if I do that? Do the math, check me on this, you get 2. So, from one perspective, that is the perspective provided by the spectral norm, the size of this graph with 3 dots, yeah, is the square root of 2. But on another hand, the size is 2. And there's just different perspectives, yeah? Different ways of measuring length. Okay. So, these are classical ways to measure lengths. So again, what this research ultimately entails is a completely new way to measure lengths. And that is provided by something called the complete homogeneous symmetric polynomials. Yeah? So that is, a mouthful, but let's sort of learn what these words mean just with examples, right? Rather than actually defining what they mean for you. Okay, we're gonna learn what they mean through examples. Okay, so HD of x1 through xn. This quite literally just means this. You're going to sum all of the degree d monomials in these variables. So what does that mean? Let's look. H2 of xy. What does H2 of xy mean? It means you're going to sum all of the degree 2 monomials in x and y. How many ways can I construct degree 2 monomials from x and y? X squared, y squared, what's the ones I'm missing? xy. That's all degree 2 sort of constructions from x and y. And lo and behold, H2 of xy is x squared plus y squared plus x squared. H3 of xy. So how many ways can I construct a monomial of degree 3 out of x and y. And you'll see that there are 4 ways. X cubed, y cubed, x squared y, xy squared. So I just look at all the ways I can construct a degree d monomial, and then I sum them. H2 of x, y, z, this one's a little more fun, because there we have 3 indeterminates, or 3 variables. Right? So again, I'm looking at all ways I can construct a monomial of degree 2 out of x, y, and z. And there are, I believe, 6 ways. X squared, y squared, z squared, xy, yz, and xz. Yeah. So if you have combinatorics, it's a fun problem to determine how many terms are going to appear in this sum in general. And that calculation is what's it called? They call it a stars and bars calculation. Is the way you would do this. Yeah, and what you would arrive at is that this term in general, for general d and general n, is going to have d plus n minus 1 choose d terms. Now, the even degree CHS polynomials, right? These are these weird combinatorial polynomials that we just talked about. These are the CHS polynomials. They satisfy a really weird property, which I'll illustrate with this example. So let's take any point in 3-dimensional space. So take any xyz in 3-dimensional space you want to. For example, you might take the point -1, 0, -100. Or you might take the point -1, -1, negative square root of 2. Yeah? Anything you want to in the entire universe of R3. So take any vector in R3. And then what you're going to do is you're going to evaluate it on this polynomial here, h2 of xy. Sorry, h2 of xyz. Yeah? Now what you'll quickly see is something weird. Look at, let's say your favorite vector in R3 is the vector -1, 2, 5. If I plug this into h2, I get 33. If I plug this vector, -1, -2, -3.5, into h2, I get 29.75. Now, the property that we're ultimately trying to discover here might not be discoverable to you in just 2 examples. Does anyone have a wild guess as to what this property is? Look, even though we have negative numbers here, what number is this? Is positive, and this is positive. Yeah? That actually happens no matter what. So this is a theorem due to Hunter that was established in the 50s, I believe. No, the 60s. It was established in the 60s. So if d is an even integer, then, if d is an even integer, and I plug in any vector into the CHS polynomial, I'm guaranteed to get something non-zero. Moreover, it's only 0 when I plug in the 0 vector. And that has, that should be sort of resembling a length in a sense, right? Think about length. Length is always non-negative. And it's only 0 if I plug in the 0 vector. Yeah? So it occurred to someone, not to myself, but to someone, that perhaps this thing is defining a norm. Yeah? And that's the case. It is defining this, it is defining an abstract notion of a norm. So this was established by myself and some colleagues in 2022. Suppose that d is even. So if I define this function, right, in which lambda 1 to lambda n are the eigenvalues of this adjacency matrix. Well, okay, here it's not necessarily an adjacency matrix, just any matrix, any real symmetric matrix. Then it's going to satisfy these 3 properties. And these are the 3 defining properties of a norm. What does this mean? The first property. It means, right, because when you see this notation, right, just think about it as length, right? This is saying or you can think about it as a size or length. This is saying the size of a matrix is always non-negative. That makes sense, as it should. So the size of a matrix is always non-negative, and it's 0 if and only if A is 0. Yeah. So the size of a matrix is non-zero, and it's 0 if and only if the matrix is actually the 0 matrix. What does this say? This tells me about how things scale. So this says the length of a scalar multiple of a matrix is the absolute value of the scalar multiplying the size of the matrix. Right? And this is similar to how lengths scale right? Like how's the scalar multiplication works with lengths of vectors. And then, what is this one called? The triangle inequality. Yeah? Lengths always have to satisfy the triangle inequality. This is the one that's really hard to prove. These other ones aren't so bad. Yeah? You can do this for homework. This one's hard to prove. Yeah? That's the hard one. Is anyone, I guess, who proved that? I proved it. Yeah, okay. Okay, so suppose G is a graph with eigenvalues lambda 1 to lambda n. So I have this new norm. Remember, once we have a norm, we can construct, or we can define a norm on graphs. Right? So I suppose I have a graph with these eigenvalues, lambda 1 to lambda n. So this is how I define this new norm, which I'll call the CHSD norm. What I do is I simply take the eigenvalues of the graph and I plug them into one of these polynomials. Let's do an example. The CHS2 norm of this graph here, right? This is the graph that we've come back to a few times now. The eigenvalues being negative root 2, positive root 2, and 0. If I plug that into H2 and then take a square root, I'm going to get the square root of 2. So this actually agrees with the spectral norm. So the spectral norm and the CHS2 norm of this graph are exactly the same. Okay, let's look at these examples, right? Well, this row illustrates the example we just looked at. This bottom row is now a different example. So this is a graph of what order? Order 3. I obtain a 3 by 3 matrix called the adjacency matrix. That's the adjacency matrix. The eigenvalues, if you were to work out the calculation and looking at the characteristic polynomial, you would get 2, negative 1, and negative 1. The spectral norm, which is highlighted in this column here, is the largest eigenvalue. The largest eigenvalue is 2. The Frobenius norm, that's the sum of the squares of the eigenvalues. If I square 2, square negative 1, and square negative 1, add them together and take a square root, what am I going to get? 4 plus 1 plus 1, I get the square root of 6. And then finally, the CHS2 norm. The CHS2 norm requires that I plug in these 3 eigenvalues into H2 of XYZ, essentially. Yeah? Remember, that was the polynomial that had six terms in its expression. Right? And now if I do that, I would get the square root of 3. Okay. Let's see how I do it. All right, so what I can do now is talk about some of the progress that we made in the paper now. Yeah? Or the results of our paper. Okay. So the first is illustrated with this table. Look at these graphs here. So I have one graph here and one graph here. This here is a graph of order 6. This is also a graph of order 6. Now, mind you, this is not a connected graph of order 6, but nevertheless, it's a graph of order 6, and I have a graph of order 6. And here I have eigenvalues for each of the graphs. Now, what is one interesting property about these eigenvalues? They are distinct eigenvalues. Yeah? The eigenvalues are distinct. However, what happens if I take their absolute values? So if I just take the absolute values up top and I take the absolute values on bottom, what's going to happen? They're going to agree. Yeah? So what that's telling me is that these classic norms cannot distinguish between these two graphs, precisely because the classic norms are defined in terms of these absolute values of their eigenvalues. Right? Think about it. The Frobenius norm, what am I doing? I'm taking the sum squares of the eigenvalues, which is tantamount to looking at the absolute values and squaring them, because when you square a positive or a negative number, you get something positive. Yeah? And similarly for the spectral norm, because the spectral norm is the largest eigenvalue of the graph, but that's kind of a lie. The spectral norm is technically the largest singular value of the graph. Now it just turns out that there's this huge powerful theorem called the Perron-Frobenius theorem that guarantees that the largest singular value is actually the largest eigenvalue. That's a very non-trivial theorem, right? So it's somewhat of a lie to tell you that the spectral norm is defined in this way, but that's not a lie, because that's actually, computationally, that's what you do. You look at the largest eigenvalue. Nevertheless, the graphs here and here are indistinguishable by these classic norms. But look at here. If you look at the CHS6 norm, they are distinguishable, and that's because the these new norms depend on eigenvalues, whereas these classic norms do not. They depend on their absolute values. And that's why these norms are so bizarre, because like you have so many classic norms that come up in the study of matrices, and none of them use eigenvalues. Yeah, they're all in terms of these things called singular values, which for our case just turn out to be absolute values of eigenvalues. Yeah. So graphs with distinct eigenvalues but with the same absolute values of those eigenvalues are called non-cospectral, singularly cospectral. So non-cospectral meaning that the spectrum is different. Singularly cospectral means that the singular spectrum is the same. Yeah. So it's just a fancier way to say your eigenvalues are different, but when you take absolute values, they're the same. Yeah. These are singularly cospectral, non-cospectral, because the eigenvalues are different, but when I take absolute values, they're the same. Right? So here's our theorem that I proved with the undergraduates. Suppose G and H are non-cospectral, singularly cospectral. Then you're guaranteed the existence of an even integer bigger than root of 6 for which these norms are distinct. Yeah, you're always guaranteed this. So that was our first result. Okay, now let's see. Okay, okay, suppose, okay, so here's an outline of the proof. I'm going to assume that I have my two non-cospectral, singularly cospectral graphs. I'll call them G and H. Yeah? So these graphs G and H, they have different eigenvalues. So I'll denote these distinct eigenvalues, lambda 1 through lambda n, and mu 1 through mu n. These are distinct now. However, I know that when I take their absolute values, those numbers are all going to be the same. Okay. Now, there must exist a smallest integer k bigger than or equal to 3 for which this number is not equal to this number. Yeah. Now, why is this true? This boils down to essentially a fact from spectral graph theory that says essentially that graphs have the same spectrum if and only if these functions are going to be the same for all k. Well, technically for k bigger than or equal to 3. Okay. Now the idea is quite simple. You expand these CHS polynomials, right? These are polynomials. You can expand them in terms of these types of functions. These are called power sums, and you expand these polynomials in terms of these functions. That's basically the idea. It's a very it's not a terribly complicated proof. And then after that, you just choose d to be 2 times k, and that essentially is the idea of the proof. In fact, the hardest part of the proof is actually showing that you can in fact expand these polynomials in terms of these functions. That's non-trivial, but it is an established result in symmetric function theory. Okay, so the main highlight of the paper is what I'm going to talk about now. Okay, so let's define a family of graphs called the paths. This is p sub 2, this is p sub 3. Does anyone have a guess as to what this is? That's p sub 4. Yeah? So p sub n has n nodes and n minus 1 edges. 2 nodes have 1 edge and n minus 2 nodes have 2 edges. These criteria determine uniquely this family that we call the path graphs. The complete graphs, these are another famous and very important family. K3, this is K4. As you might have guessed, this is K5. So in a complete graph, K sub n, you have n nodes, and for each possible edge that you can draw, you must draw, essentially. Right? So in how many ways can I draw edges between n nodes? There's n choose 2 possibilities, right? Because how do I draw an edge? Well, I have to choose 2 nodes to do it. Yeah, and that tells you that there has to be n choose 2 total edges. Okay. Consider the family of all connected graphs of order n. Okay, all connected graphs of order n. Now, there are approximately 2 to the n choose 2 divided by n factorial such graphs. Now, interesting, this is not known. Nobody in the world knows how many connected graphs of order n there are. Yeah? But approximately, it's known to be, close to that number. What happens to this thing as n goes to, like, as n gets bigger? It's so big. It's ridiculously huge. Yeah. And then I was just curious, I was like, okay, let's suppose I wanted to ask a computer the following question. Okay. Let's just do this. Let's suppose n is 17. Yeah? Let's suppose n is 17. Which, it's not that big. It's like you have just 17 dots. Yeah? And you're drawing edges between them. 17 dots. Yeah? And you want to ask this very simple, it's a very simple question. Out of all of the graphs that I can possibly draw with n nodes, yeah, which of them has the largest spectral norm and which of them has the smallest spectral norm? Yeah? So it's a very simple question. But ultimately, like for example, a computer cannot do this. It's too much, right? Like my laptop, right? I think the strongest supercomputer in the world, I think, is it Frontier at Oak Ridge? I think that's probably up there. Yeah. I think that can do like a quintillion calculations per second, and that's a million. It's about 1 million or 10 million times faster than my laptop, right? So when I was kind of playing around with these calculations, I wanted to see how long it would take the Frontier, or United States Frontier, to check all graphs of order 17. It was something like 8 years if it was running straight. So it's not an easy, well, it's a simple question, but it's not necessarily easy to answer, which is always remarkable as to how people prove these things. So in 1957, Kolatz and Sinagowitz proved that, okay, if you have a connected graph of any order n, the smallest spectral norm is always given by the path, and the largest spectral norm is always given by the complete graph. Always, always, always. And this is true for any n. Okay, so the highlight of this paper that I worked on with these undergraduates is the analog of this theorem for the CHS norms, for these new norms. So interestingly, these CHS norms satisfy the exact same bounds. And so here's our theorem. If G is a connected graph of order n, and D is an even integer, then the same bounds hold. The CHS norm of my connected graph G has to be bigger than or equal to the CHS norm of the path and bounded above by the CHS norm of the complete graph. Okay? So it is the genuine analog of this theorem by Kolatz and Sinagowitz from 57. Okay, heuristic proof time. Okay, so suppose I have eigenvalues of my graph, yeah, lambda 1 to lambda n. Again, I expand the CHS polynomials in terms of these symmetric polynomials here, these power sums they're called, yeah? Now, so that again isn't, it requires, some work to do that, but the really difficult part in the proof is this, that this quantity is minimized by the path for each j, and this quantity is maximized by the complete graph for each j. Yeah? But this essentially is the outline of how the proof goes. And moreover, it's important that the coefficients of these polynomials or the coefficients of these polynomials in the expansion of the CHS polynomials are positive, so that I can use these results here. But that's essentially the idea of the proof. Okay, so what have we done? We have found the extrema of this norm as G ranges over all connected graphs of order n. Yeah? So essentially at the end of the day, what did we do? We looked at all graphs of order n, right? Which there's gajillions of them. Gajillions and gajillions. Yeah? And we found the smallest one and we found the largest one. Yeah? Where largest, again, is with respect to this new notion of size. So we found the smallest and we found the largest. So, future work. Can we find the extrema as G ranges over a different family of graphs? So instead of ranging over all possible families of graphs, what you want to do is just look at certain subfamilies. Yeah? So for example, you could look at things like trees. Well, okay, so we already solved that problem. I just didn't talk about it here, but we solved the problem for trees also. Yeah? So if I look at all possible trees, which is just a special type of graph, if I look at all possible trees, I know which one is the smallest, I know which one is the largest. And again, it's miraculous because there's gajillions and gajillions of trees, just like there's gajillions of graphs. Nevertheless, there is a something that I would like to work on in the near future, is to answer this question for the family of what are called complete K-partite graphs. Yeah. So let me explain what that is here really quickly. So a complete K-partite graph of order n. Well, it has order n, so I have n nodes, and I partition these nodes into K subsets. No edge exists between nodes in the same subset, but if an edge can exist between nodes in distinct subsets, then it must exist. So here's an example. This is a complete tripartite graph of order 1, 2, 3, 4, 5, 6. Yeah? So in this context, K is 3, N is 6. So what am I doing here? I'm partitioning the nodes into 3 different subsets, where I'm indicating those by color. So I have pink, light blue, and dark blue. Right? So the subsets of my partition have sizes 1, 1, and 4. Yeah? And so that's why this graph is denoted K, 1, 1, 4. So this is, again, an example of a complete tripartite graph of order 6. Okay. Now, in general, the complete K-partite graph, K sub n sub 1 all the way to n sub k, has these things called partition numbers, right? The partition numbers in the previous example were 1, 1, and 4. Here my partition numbers are n1, n2, up to nk. C sub nk. So I'm just defining another family of graphs. This is defined by taking k, 1, 1, 1, 1, etc., until you get to n minus k plus 1. That graph that we were just looking at was one of these types of graphs. It was C sub 6, 3. Yep. Now, in case you're interested, these are called the complete split graphs. These are called complete split. That's why we use the letter C. Another super duper important type of complete K-partite graph. Okay, so I'm going to set A to be the ceiling of n choose k. Right, that's the smallest integer that is bigger than n divided by k. Similarly, B is going to be the floor of n divided by k. What is that? That's the largest integer smaller than n divided by k. I always get those mixed up. R is n modulo k. And again, I'm going to define a graph, which is going to be a complete K-partite graph by taking k with the partition numbers, A appearing R times and B appearing K minus R times. Now, this is called the Turan graph. Yeah? And here's an example of a Turan graph. Yeah? So the very first examples that I gave you of graphs, it was the second example. When I asked which graph of these is larger, well, this is the one that appeared on the right. Yeah, if you remember, you got a good memory. This is T sub 6, 3. Yeah. So here's our conjecture. The conjecture is that if I look at any complete K-partite graph of order n, yeah, and D is an even integer, the largest it can possibly be, excuse me, the maximum is obtained by the Turan graph, the minimum is obtained by the complete split graph. Okay, now one interesting thing that I think is, to me it's really interesting, is that, excuse me, this conjecture, I'm like 95% not approved. Yeah, 95%. Maybe actually higher, maybe more like 98. I'm like 98% sure I not approve it. And incidentally, the proof, let me get some water, sorry. Math is like too exciting. Okay, hold on. Okay, so the interesting fact here is that the proof of this theorem, right, or what I believe would be a proof, was again, like I said, 98, maybe 99% certain I know how to prove this, is actually so much easier than the proof that we did in the paper for the general case, for looking at all graphs. Yeah. So that's why I think it would only take students, I think it would take them a semester to get through this. Yeah. A semester of like an independent study, for instance, and they would be able to solve this problem. Yeah. And that's because the proof of this fact doesn't rely on the symmetric function theory at all, in any regard. Yeah, it doesn't rely on the symmetric function theory in any regard, right? And that was the biggest hang-up in my or the biggest hurdle, I should say, in working with these 6 undergraduates was learning the symmetric function theory, because that's it's advanced, and it just took us a lot of time to do. Yeah, and these were students that were fresh out of linear algebra, so they went to the deep end right away. But we learned a lot. We had a lot of fun, and I'm really excited about finding students to solve this problem. Thank you.
Right,
Are there any questions? Yes, Tim.
Does any of this work with directed graphs, or does it?
Well, you can still ask the same question. You can say, if I have a norm, you can still look at all directed graphs and still ask about the smallest and the largest.
Okay.
But to my knowledge, that type of question hasn't been answered in any aspect because of how much it complicates things.
Yeah, that sounds horrible. It's no longer symmetric graphs. So
Well,
no-
yeah, that's true. That's true. Yeah.
Yeah.
See, the thing though too. Yeah, you can still define a notion of a length for something that is not a symmetric matrix. Like you can, like this Frobenius norm works for any type of complex matrix, any type. It doesn't matter. So you could define a notion of a length for a directed graph. However, these norms that are new that were published in the paper that I co-authored, the CHS norms, those have to be defined on. No, actually, no, that's not true. No, yeah. The answer is yes. You can actually use those to look at directed graphs also. Yeah, but it's not something I've thought about. That sounds really
It sounds,
complicated.
yeah.
That sounds way too
Insane.
complicated. Yeah.
Yeah.
Well, one step at a time. Next step is to prove this conjecture, which I'm gonna say I'm like 100%. I'm basically 100% sure it's right.
Yeah. The longer we wait, the more sure you are. So
Yeah. Well, no, in fact, like I started to prove it. I said, "Oh, I know how to prove it." I started, and I said, "Wait, what am I doing? I'm gonna, this should be something that an undergraduate explores." So I stopped. But I'm pretty sure it's true.
But are there relationships between the different kinds of norms? Like, is one always bigger?
Okay, so yes,
Are there
yes.
some types of graphs where one's bigger and other types of graphs where another?
Okay, so you're working on a finite dimensional vector space here, like the space of n by n real symmetric matrices.
Yeah.
And whenever you have a norm on like a finite dimensional space, you always have what are they called? Equivalence constants, where you would say something like So you always have things like let's say if I take the Frobenius norm, this is always less than or equal to some constant times, we'll say the CHSD norm. Yeah, but determining these constants is incredibly difficult. It's very difficult. Very, very difficult. Like it's astonishingly difficult. Just because these norms are they're very algebraic. It's very complicated. Yeah. Right, because you have to think about, well, how can I bound the square root of the sum of squares by this complicated polynomial of degree to d, and then taking a dth root, and then so that it's optimal. It's complicated. It's a bit difficult. In fact, this problem is a very famous problem that shows up a lot in probability, called the Khinchin inequality. Yeah. So there's actually lots of research about getting these types of inequalities called Khinchin inequalities.
For the standard norms.
No. Well, I'm getting like way ahead of myself. The answer to your question is like it's difficult.
Yeah.
Yeah. Sorry, got it.
I accept that answer.
Yeah. It's really difficult.
Do we have any other questions for Dr. Chavez?
I have a question.
Yeah.
How do you build or construct a matrix with a 1, 2, 3 triangle and 1, 2, 3 triangle? Because I
Oh,
can
like
show-
disconnected?
Yes. How
Yeah.
does it go like in a?
Oh, okay. So the interesting thing is, yeah. So whenever you have two disconnected graphs, The adjacency matrix is gonna be a block matrix, where the blocks are the adjacency matrix for the graph started individually.
Okay.
Yeah. So that's why if you go back,
Uh-huh.
yeah, well, if you go back to the slide, you'll see
Yes.
that it's a block matrix,
Okay.
and each block is gonna be the adjacency matrix of the graph just by itself.
Okay.
And then that lets you see in that example, because I didn't compute this eigenvalues by hand, I just said, well, I know this is a block matrix, and
Uh-huh.
so I just multiply the eigenvalues by 2, or I made their multiplicities by 2, and that gives me the eigenvalue.
Okay, thanks.
It did take a long time to make those graphs.
Okay.
Yeah.
though. It took a really long time.
And
Yeah, to make the
does-
pictures, yeah.
Does
Did
this
you-
method have any application outside the math? So
That's outside the pure math?
like
There has been,
technologies?
some top application to things like, portfolios in economics or something. I'm not too versed in that aspect of it. But that's something that, maybe in the future we can talk about, or like, I can think about. Like my interest is first and foremost in just pure mathematics, is where my interest lies. Sometimes if I hear of an application, I get kind of bored of it, right?
Yes, I see. That's okay.
Okay, no, I'm just joking. That's not entirely true.
You
But
would make a good physicist.
Yes.
no, I would not make a good physicist. No, I mean that is an interesting question. That's something I've come back to and thought about.
Yes.
But applications like maybe in the regard you're thinking of, probably nothing that I can think of. But there's certainly other applications to more pure mathematics. Yeah.
All right.
Like for one example, one thing that I did do actually with another undergraduate student, one that was a little bit more advanced who was now in graduate school. We also submitted a paper for publication where we looked at these norms, right? Where we endowed the eigenvalues with random structure. So we looked at like these Erdős-Rényi random graphs, and we computed the distribution for the norms essentially as n goes to infinity. So as the size of the graph goes to infinity, and we were able to get like actual limiting distributions, which was really that was a really fun project. So that's maybe application-y, I suppose. Yeah.
Okay.
Yeah, I mean, like the founder, the founder of random matrix theory is a physicist, Wigner. So yeah, so that's like as close to physics as I've gotten in a long time. Yeah.
Thank you.
Outside of the calculus class, maybe.
Yeah. Okay. Yeah. I suppose. Yeah. Yeah. But you know, I do appreciate physics, but it's also very intimidating to me personally because I do not understand most of it.
Me
So-
neither.
Yeah, that's exactly the response I give when people tell me that math is difficult. I tell them like, no, it's really hard. Yeah, it's very difficult. Yeah, yeah, but that's the appeal to it of it all. Yeah. All right, so thank you for coming. I really appreciate it.
Final questions? All right, let's thank Dr. Chavez again. Students, make sure you get your forms, and then your